Okay, so Chapter 9 deals with rational functions. Again, just like with all of our other chapters that we work for, when we're looking at graphing, we're always looking at the parameters of a, b, h, and k. And that's what we're going to be doing with this. Now, a rational function is just basically a fraction with a variable in it. So we're going to look at graphing these, and we've done some rational function graphings already, so it's not anything really brand new. We're just going to apply a few extra things to it. So our general form for a rational function is y is equal to a over x minus h plus k. This is the form we want a rational function to be in when we graph it, and you'll see in examples coming up that we're going to manipulate equations so that they are in this form. Sometimes you'll also see it written as y is equal to a times 1 over x minus h plus k. It means the same thing. The a value is still telling you your vertical stretch. Your h value is still telling you if your graph is moving right or left, and your k value is still going to be determining your up and down. With rational functions, though, they also have a couple of the h and k values are going to also tell you where a few other key points are on your graph. Okay, so let's look at our first example here. It says analyze the function y is equal to 6 over x using a table of values and graph it. Okay, so we're just looking at a basic rational function here. We're going to use a table of values to see what happens when we punch in some of these values. So if I do my table of values along the side here, x and y, I'm going to start with some fairly large negative numbers and move to some fairly large positive numbers. So the first few I'm just going to show you how I calculated. The rest of them I'm just going to write them in. So if I use negative 60, 6 divided by negative 60 leaves me with negative 0.1. If I do half of that, negative 30, 6 divided by negative 30 leaves me with negative 0.2. If I go to negative 12, and you can see I'm picking numbers right now that are multiples of 6 so that we can get a nice round number for an answer. So negative 12 would leave me with negative 0.5. Negative 6 would be negative 0.1. Sorry, not 0.1. Whoops, I put an equal sign and everything in there. Negative 6 would be a negative 1. Negative 1 would be a negative 6. Negative 1/2 is negative 12. 0, if I put 6 divided by 0, that of course will give me an error in my calculation, so that's undefined. And what we've noticed so far, whenever we're graphing and we have an undefined, you have an asymptote. So this is going to give us a vertical asymptote. Okay, now I'm going to work my way back up. 1/2 gives me 12. X value of 1 gives me a 6. 6 gives me a 1. 12, 0.5 or a half. 30 is 0.2, and 60 is 0.1. So if I go to graph this, use black on here. Whoops, I don't want. Oh, I'm going to move that down a little. I put it a little bit higher than I wanted it. So if I put this over here and I start graphing these, when my value was at, I should make my, whoops, this was my y's and these are my x's. So when my x value was a fairly small negative number, my answer was fairly close to 0, but not quite at 0. So at negative 60, it was at negative 0.1. So about there. Okay, if I call this negative 60. So this over here, I'm going to call it 60. At negative 30, I was at negative 0.2, so you can see if this is negative 30, I'm getting a little bit further away from my 0, but not real far away from my 0. Negative 12, I was at half. So negative 12 is going to be about there, and about a half. I'll call this 0.5. At negative 6, I was at negative 1. So that's about halfway between there. So negative 6 and 1 would be about here. Negative 1, I mean. At negative 1, I was at negative 6. So we'll pretend here that I'm got this evenly spaced, but I'm going to be about right there. At negative 1/2, I was at negative 12. So you can see here, my graph it gets close, and then it starts curving, whoops, and going down and getting close again to that 0 there. Now on the other side then, if I was at 1/2, so if I'm thinking of on my x value, I'm at a half, it's going to be here. I was up at 12. When I was at 1, I was at 6. When I was at 6, excuse me, I was at 1. So I don't know, we'll say 6 is about there. When I was at 12, I was at a half. When I was at 30, I was at 0.2. When I was at 60, I was at 0.1. So again, you can see it's getting close. It gets really close to my zeros, but it never touches them. So if I take a look at this based on my values and my graph, my non-permissible value then is 0. I never, on that x, I never get 0. Remember, non-permissible value always comes from your denominator, putting your denominator equal to 0. Okay? So we can calculate that by putting our denominator not equal to 0. So if I looked at my equation that I had, y is equal to 6 over x, x is in my denominator, I'd put x not equal to 0, so that's where my non-permissible value is. Behavior near that non-permissible value. So my non-permissible value is x is not equal to 0. So my end behavior is, okay, what happens to the end of that graph? Well, what's happening here is as x is getting closer and closer to 0, okay, so I start here, it was at, where am I? It was at negative 60 going to negative 30, then to negative 12, negative 6, negative 1. What's happening is that my y is becoming, the absolute value of the y is becoming larger and larger and larger. So if I look here, as my x is getting closer to 0, my y's, if I take a look at the absolute values of these, so if I put absolute value signs around them, it's getting bigger. I'm going decimal 1, decimal 2, decimal 5, 1, 6, 12, and then as these numbers here got closer to 0, 1/4, 1/8, and so on, these values on this side would be getting larger and larger and larger. So my description for my behavior near the non-permissible value, as x approaches 0 or gets closer to 0, the absolute value of y becomes very large. Okay, my end behavior. So the end behavior is when you're finished filling in your graph here, basically. So as you're looking at your x values, as your x numbers are getting bigger, your absolute value of y then is getting closer and closer to 0. So at 6, my absolute value of y was 1. At 12, it was a half. At 30, it was 0.2. At 60, it was 0.1. If I went to 120, that's going to be 0.05. If I go to 240, it's going to be 0.08, and so on and so on and so on. So that number is getting closer and closer and closer and closer to 0, but it's never going to 0. So if I look at my graph here, as my numbers are getting bigger, my x's are getting bigger, my y's are getting closer to 0, so my graph is coming closer and closer and closer here to 0, but never, ever, ever touching it or crossing it. So as x gets larger, absolute value of y approaches 0. So what is my domain? Well, for my domain, I can use any real number that I want, except for 0. So I write that as x is not equal to 0, that x is an element of real numbers. So every single real number except for 0. What is my range? My range is my y's. If I take a look at my y's get close to 0, but they never equal 0. So y is not equal to 0, and y is an element of real numbers. So every single real number can be used for y except for 0. My vertical asymptote, well, that was where my graph was undefined. When I substituted an x in, what was my y value? So when I substituted 0 in for my x, and I hit an undefined, then I have a vertical asymptote, or wherever that undefined is. The way I find it is by putting x not equal to 0 in the denominator. So my vertical asymptote in this case would be here at x not equal to 0. My horizontal asymptote then, what color can I use for that one? Maybe I'll use red. I want to change my, pen thickness. So my horizontal asymptote then is oh, why did it pick up green? Oh, because my horizontal asymptote is going here then, and I could use the same color as the purple, but I just wanted you to see the difference. Is right there at y is equal to 0. So remember, your vertical asymptote has to deal with your NPV value, your non-permissible value. Your horizontal asymptote is going to be a little bit different, and you'll see in our next few examples what I mean. Okay, vertical asymptote. So this says intro to calculus. Don't let it scare you. It's just going, when you're working on some problems in calculus, you'll come across this type of thing. This is how they solve them in calculus. So your vertical asymptote, in order to find that, you need to make your denominator equal 0. Your horizontal asymptote then, no, this is missing, but it's missing on mine, but it'll be on yours. It says, look at a trend on the graph, substitute in very large values for x, and reduce your major powers and substitute in some very large values. So those are just the steps. So for a horizontal asymptote, if I had this, if I had 2x over x plus 1, my vertical asymptote then is when I take my denominator and put it equal to 0. So I take my denominator, x plus 1, put it not equal to 0, so x is not equal to negative 1. So that's going to be where my horizontal asymptote is. Sorry, my vertical asymptote. My horizontal asymptote, according to the instructions that aren't here that got covered up or chopped off somehow, it says, look at the trend, substitute in very large values for x, so that's one way of doing it. The second way to do it is to reduce your major powers and substitute in very large numbers. So if I look at my major powers, in my top one here I have 2x, and in the bottom one I just have a power of x. Well, my x's will cancel, so my horizontal asymptote is at 2, or at y is equal to 2. I could substitute numbers in for that instead, and I would find the same thing, that as I'm putting in values here, my numbers are getting closer to 0 or to 2, but they're not touching 2. So like if I had 2 over 8 times 8 is 16, 8 plus 1 is 9. 16 over 9, well, that's just about 2. It's because 18 over 9 would be 2, so it's just short of being 2. If I substitute in 20, 2 over 20 is 40, or 2 times 20 is 40. 40 plus 1 is 41. Sorry, 20 plus 1 is 21, so 40 over 21 is just a little over 2. So it's getting it's close to 2, but it's not exactly 2. Okay, if I had x plus 1 over 3x squared. Well, my vertical asymptote, that's easy. 3x squared is not equal to 0. So if I divide by 3, I have 0 divided by 3 is 3. I'm left with x squared not equal to 0. Square that. So x is not equal to 0. So that would be my vertical asymptote. My horizontal asymptote then, if I try this, I could take my major power, so x over 3x squared leaves me with 1 over 3x. So again, I could set that at not equal to 0, so that would leave me with 3x not equal to 0, x is 0. So my horizontal asymptote, is at, and then even though it's an x there, it's going to be, because it's horizontal, it's at y equal to 0. So, and I can try in some numbers. I can try some numbers there. If I went 30 plus 1 is 31, 30 squared, well, that's going to be really big, but it'll be 900 divided by, or times 3 is 27, so 30 divided by 2700 is 1/900th? Close. When you substitute in, you'll see they'll get close to 0. So if I did 3 plus 1 is 4, 16 times 4 is, 48, 4 over 48. You can see my number's going to get close to 0. It'll jump over 0 at one point and get larger if I substitute in negatives. But it's not going to touch 0. Okay, so let's apply some of this information. So it says sketch the graph of the function y is equal to 4 over x plus 1 plus 5. Use transformations and identify the important characteristics of the graph. I see it didn't erase this very well from last time. So knowing my basic transformations from that first page, my a here is a 4. So that means I have a vertical stretch of 4 times y, because that a value affects the y, ay, right? My h is equal to, it's a plus 1 there, so it would be a minus 1. So that means I'm going to go left 1. My k is equal to 5. So that means that I'm going to go up 5 units. Okay, and I could do a table of values to find some values, but I'm just looking for a sketch of this. So if I were to draw this, remember my general graph would be, or my normal graph, basic graph, whatever you want to call it, would be y is equal to 1 over x. So y is equal to 1 over x would be like this. Whoops, pretend that gets closer there. If I'm doing y is equal to 4 over x plus 1 plus 5, using my, what do I want to do? I'm using my translations here. I'm going up 5 and to the left 1. So up 5. This is blue, so let's do red. So up 5. So my new that would be my new horizontal axis. To the left, -1. That put me there. So then this is my new, whoops, pretend that's going through 1 there. Obviously my alignment isn't that great. Would be -1. So now if I go to draw this, it's going to be stretched a little bit, my values, but it's still going to have the same general shape. It's going to go here, and it's going to go here. Okay, so if I think of this as being on my x and y, if I just draw it on my general x and y, without showing all of those shifts, it's going to be going, whoops, and I shouldn't have done, oh no, I'm okay there. It would look like this. With a I would have it, and this is, well, I'm going to have to fix my graph, but pretend this is straight. It would look like that. This should be, my dotted line there should be a straight line. I should have drew that in first. So if I take a look at this, where are my asymptotes? My vertical asymptote here is at that x is equal to -1. I'll do this in red because I'm looking at my red graph. So my vertical asymptote is at x is equal to -1. My horizontal asymptote going across this way is at y is equal to 5. So if I take a look at this, what my vertical asymptote and my horizontal asymptote, those values coincide with my h value and my k value. So the vertical asymptote is actually the same as x is equal to h, and my horizontal asymptote is the same as y is equal to your k value. If I tried to do this algebraically, and there will be questions where it asks you to do it algebraically, I would have, for my vertical asymptote, I would take excuse me, my denominator and put it not equal to 0. So x plus 1 is not equal to 0. X is not equal to -1. Okay. That worked for that one. Horizontal asymptote, if I were to substitute in, or if I look at my major points there, I have x plus 1 over 5. Well, this is just going to be, because remember this value here gets close to 0. 4 over 0 doesn't work, but I'm left with this plus 5. So a simple way of calculating your vertical asymptote is to take a look at your h value, and your horizontal asymptote then is to take a look at your k value. So what is my non-permissible value? Remember, non-permissible value has to deal always with the denominator. So my non-permissible value is x is not equal to -1, so that's this calculation here. My behavior near that non-permissible value, so as x is getting close to -1. So -1 is here. As x gets close to it, what's happening to my y? Absolute value of y, even though it's going down this way, but the absolute value of that is greater. If I look at it over here, as it on the top part of this graph, as it's getting closer this way to that non-permissible value of -1, my y values are increasing. So as x approaches my NPV, and in this case, -1, my absolute value of y, and I always look at the absolute value, becomes larger. What is my end behavior? So the end behavior is as x gets bigger, what happens to the absolute value of y? So as x is getting larger here, going across this way, x is getting larger. My absolute value of y gets close to 5. Okay? It's coming closer and closer and closer to 5. And then if I look at it on this side, as my x is getting larger this way, it gets close to 5, but it doesn't touch it. So as I'm going this way, my x's are getting closer to 5. My y's are going down, down, down to that 5 value here, but not touching it. Okay, so what is my domain? The set of values for x such that x is not equal to -1, but it can be any other real number. My range then is the set of values for y such that y does not equal, 5, not a -5. Y is an element of real numbers. So my vertical asymptote, I calculated up there, I showed you up there, x is equal to -1. My horizontal asymptote is at y is equal to 5. Okay, next example. It says, graph the function y is equal to 2x minus 2 over x minus 4. Identify any asymptotes and intercepts. Okay, so the first way we're going to do this is, I don't know why I'm missing letters all over the place here, is the calculus method. So what we want to do there is we want to take a look at it. We want to find our y-intercept. Finding the y-intercept will help us to know where that graph is going to cross, or if it's going to cross. Sometimes it won't cross the y-axis, but we'll try it and see. So the y-intercept, that means we substitute x is equal to 0. So I have y is equal to 2 times 0 plus 2. Whoops, I don't need a bracket there. Over, 0 minus 4. So 2 times 0 is 0, plus 2 is 2. On the bottom, 0 minus 4 is -4, so this is at -1/2. So my y-intercept would be at 0 and -0.5. So the next thing I want to do then is I want to see if there is an x-intercept. So I substitute y is equal to 0. So I have 0 is equal to 2x plus 2 over x minus 4. So to solve, I would multiply both sides by x minus 4 to get rid of, oops. So that and that cancel. This is still 0 is equal to 2x plus 2. So -2 is equal to 2x. If I divide by 2, -1 is equal to x. So that means that my x-intercept will be at -1 and 0. So now I want to find my vertical asymptote. So this equation here, because it's not in that form, it's not in Okay, well, I have a 2x plus 2 there. I don't have it written like that, so I can't just pick my h and k values out of there. So my vertical asymptote then, I take my denominator, put it equal to 0. So x minus 4 is equal to 0. X is equal to 4. So I know I'm going to have a vertical asymptote at x is equal to 4. My horizontal asymptote then, that's where I take my major terms and see what happens. Whoops. Terms. So my major terms here are, they're the ones with the variables in them, 2x over x is equal to, those will cancel, so it's just 2. So my sketch of this would look like this. So this is just going up by ones here. So these are negative values going down this way. So first thing I'm going to draw in is my vertical asymptote. So I have a vertical asymptote at x is equal to 4. So 1, 2, 3, 4. It's going right through here. Horizontal asymptote is at y is equal to 2. Oops, I didn't finish. So that's 1/2, 1, 1.5, 2. Pretend that's nice and straight. I should extend that to go that way. Okay. Now I know that this is going to cross my graph at 0 and negative 0.5. So right over here. And then it's going to cut also at negative 1 and 0. So that's right over here. So because this is on, if I'm thinking of this as my new axis where I can't do crossing, so it's going to go look something, whoops, pretend that goes through that point. And then this one will be going to look like that. That's the sketch of it. It's not very accurate, it's not very pretty, but it shows me my major things. It's giving me x and y intercepts because there are some. It's showing me where my asymptotes are and which sides the rest of the graph would be on. So method number 2 is to put it in the form y is equal to a times x minus h. Y is equal to a over x minus h plus k. I might have said that the first time, I can't remember. Okay, so just like in method 1, we're going to find the x and y intercept. Okay, I've already done that up there, so I'm not going to do it again. Then your second step is we need to do a manipulation, and this is a little bit tricky. It takes some practice. So we want to manipulate that equation so it's in the general form. Y is equal to a over x minus h plus k, because this then will give me my vertical asymptote and horizontal asymptote. So that's why we want to do that. So what we need to do then is our equation was y is equal to 2x plus 2 over x minus 4. So what we want to do is have x minus 4 be in the numerator. Whoops. Yeah, in numerator. Okay, so that means that I have to manipulate that equation somehow so that x minus 4 is in the numerator. So if I take a look at this, if I just take a look at my 2x here, and I'll put my plus 2 over here. So 2x, to get it so that there's an x minus 4 in there, what I need then is to have 2 times x minus 4. So that really is 2x minus 8. So really all I'm doing to this equation is is putting in a minus 8. But I can't just say minus 8 because that changes the whole thing. So what I have to do is I have to add 8 to the equation as well, because then I've really added nothing. So I can put this in as 2x minus 8, and then plus 8 plus 2. So even though I put a bracket around this 2x minus 8, I'm doing that for a reason. I could leave it off, and I would still have 2x minus 8 plus 2, which is still 2x plus 2. I'm not doing anything to the bottom, so I'm just going to leave my bottom as, oops, I'm just going to slide this up, x minus 4. So by putting my 2x minus 8 in a bracket here, I can GCF there, and I have 2 times x minus 4 plus 8 plus 2 means I have plus 10 over x minus 4. So now that I have an x minus 4 in the top and an x minus 4 in the bottom, I can do some canceling. But before I can cancel, and I wrote kind of big here, so I'm going to extend my page. If I separate this to say this is 2x minus 4 over x minus 4 plus 10 over x minus 4, right? Because these are two terms, they're both being divided by x minus 4, so I can write them like that. So what happens here is I can cancel my x minus 4s from here, and I'm left with y is equal to 2 plus 10 over x minus 4. By a quick little movement here, I can switch that around to 10 over x minus 4 plus 2. This is now in y is equal to a over x minus h plus 2. So this tells me from here, I'm going to move my graph. My transformation would be moving it right 4 and up 2. This is also telling me that my vertical asymptote is at x is equal to 4, because x is equal to h, and my horizontal asymptote is at y is equal to k, so y is equal to 2. So the tricky part comes in here, where you have to do that manipulation of your equation so that you have whatever is in the denominator in the numerator. And it just takes practice to get that. Okay, example number 4. That's why there's so much room. That's where it went to. So they want us to graph these three functions. Y is equal to 1 over x squared, x is equal to negative 1 over x minus 3 squared, and hx is equal to 2 plus 5 over x squared plus 2x plus 1, and then compare the characteristics of the graphs. Okay, so our normal graph, right, would be y or f of x is equal to 1 over x. So that's the one where it just looks like that. So if I have a 1 over x squared, what that means then is that I'm not going to have any negative y values. So my graph is just going to be, oh, this is nice. Pretend that's not there. My y's are never going to be negative. So for the first one, okay, my vertical asymptote is at x squared, if I put x squared equals 0, then that means I have x is equal to 0. So my vertical asymptote is at x is equal to 0. My horizontal asymptote, I don't have any k being added onto there, so it is at y is equal to 0. So my graph for this if I want to draw in my horizontal and vertical asymptote, I'm just going to use this so I can have a lighter line. It's going to be going right through there, and my graph is going to be like this, and like this, because it's not going to be in the negatives, it's only going to be in the positives, y's. So g of x is equal to negative 1 over x minus 3 squared. So my vertical asymptote, my h value is a 3. So if I take x minus 3, put it equal to 0, I have x is equal to 3. Or if I look at my h value, it's a positive 3 when I pull it out. My horizontal asymptote, what's being added on? What's my k value? It's a 0. So that's going to look like that. This negative in front of here, all this means, if a is negative, remember a affects the y, so that means the y is going to flip. So if my y is going to flip, that means that normally when it's a squared, all my y's would be positive, but because I have that negative, that means it's going to flip into the bottom. So now this is all this is going to say is my y's are going to be all negative values. So if I draw this one, here's my normal. Okay, I'm moving right 3. I know my vertical asymptote is at x is equal to 3, so this is 3. There's my vertical asymptote. My horizontal asymptote is at y is equal to 0, so it's going through there. It's a squared, so I know my graph is going to go, and I could calculate an x and y intercept too, I guess, but why don't I do that one? So my x-intercept, that y equals 0, so I have 0 is equal to negative 1 over x minus 3 squared multiplied by x minus 3 squared to get rid of that. So I have 0 is equal to negative 1, so there is no x-intercept. Y-intercept, if I let x equal 0, I have negative 1 over 0 minus 3 squared, so this is going to be at negative 1/9. So it's, I'll do it over there, I guess. 0 and negative 1/9. So at 0 and negative 1/9, which is pretty much at 0, I'm going to have a y-intercept. So my graph is going to go like this and like this. So this is for gx. Okay, and my last one, well, I can do it underneath here, because my example 5 is actually on the next page. So my hx graph, I'll do that one in green. Hx is equal to 2 plus 5 over x squared plus 2x plus 1. Okay, so if I take a look at my x squared plus 2x plus 1, that really is a trinomial square. And remember, the trick for the trinomial square is if I take the middle term divide it by 2 and square it, I need to get the last term. So for this one, if I take my 2, which is my middle term, divide it by 2 equals 1 and square it, I should get my last term, and I do. So that means that my factor for this, I can factor this into 2 plus 5 over x plus 1 all squared. Remember, I take the sign of the middle value. So this can be rewritten as 5 over x plus 1 squared plus 2. So this means my h value is equal to h is equal to -1, so that means I'm going to go left 1, and that means my vertical asymptote is at x is equal to -1. My k value was a 2, so that means I'm going to go up 2, and it means my horizontal asymptote is at y is equal to h, so y is equal to 2. X and y intercepts. So y-intercept, again, if I substitute and try to find my y-intercept, so I have 5 over 0 plus 1 all squared plus 2. So 5 over 1 is 5 plus 2 is 7. So that's going to be at 0 and 7. My x-intercept, I have 0 is equal to 5 over x plus 1 squared plus 2. So if I move my 2 over, so I'm going to have, I'll finish it over here, -2 is equal to 5 over x plus 1 all squared. Well, that's going to give me some really wild numbers. So you can finish calculating this, but in order to finish the calculation for this, you're going to, well, in your calculators, you can graph it and find it, or you can use your quadratic formula. X is equal to -b plus or minus square root b squared minus 4ac all over 2a. We're not going to worry about it. So if I go to draw this one now, so here was my x and y intercept, or axis. I know I have a vertical asymptote at -1. So I call this -1. My horizontal asymptote was at y is equal to 2. Okay, because this is a squared, I know I'm not going to have anything going below my y-axis, and this is my transformed y-axis. And my one intercept was at 0 and 7. So here, let me extend my graph here. Okay, so if I call this, if this was 2, 4, 6, so we'll say 7 is right there. So it's going to be crossing it, and this is a really bad example, or picture, but it's going to look something like that. We know that somewhere there's going to be a point where that crosses at 0, 7. So it's done. Okay, example 5, it says, Marlis is producing a tourism booklet for the town of Atlin, British Columbia, and its surrounding area. She is comparing the cost of printing from 2 different companies. The first company charges a $50 setup fee and $2.50 a booklet. The second charges $80 for setup and $2.10 for a booklet. So it says represent the average cost per booklet for each company as a function of the number of booklets printed. Okay. So my total cost, if I'm calculating this, would be your setup plus your booklet fee. So how much does it cost per booklets? And that is based on the number of booklets you buy. So your average cost then is going to be your total cost divided by however many booklets you print. So for my first one here, I'll do my A. So my average cost is the total cost over the number of booklets. So my total cost is the setup fee. So for the first one, it was $50 plus $2.50 times your number of booklets. And then to find the average cost, I would divide by X. So if I call this my Y1 equation, my Y2 then, the second one, would be at $80 for the setup. So it costs more to set it up initially, but less to print per booklet, $2.10 per booklet, divided by the number of booklets. So if you go to graph these, and probably the easiest way to graph these is to put them into your calculators. Do your Y1 equals 50 plus 2.5x over x, Y2 equals 80 plus 210 over x, and you'll get your two graphs. So you draw your graphs, and because we're not going to have any negatives, you're not going to spend negative money, and you're not going to print negative books. Your graphs are going to look something like this. And eventually these two get really, really close to each other. So this would be my Y1 graph. This would be my Y2 graph. Okay. So that's my B. This is what the graphs would look like, and the best way to do that is on your calculator and then just draw it. Okay, the C part says, explain how the characteristics of the graphs are related to the situation. So this is showing you the average cost, right? And this is, whoops, cost. This is your number of booklets. So what's happening here is the fewer booklets you print, the higher the cost is to print these. So if you have a smaller amount that you're printing, it's going to be fairly expensive to do this. But it gets cheaper the more you print it. So as I print more and more books, so as I'm going this way, my cost is dropping and dropping per booklet. So my C, the graph shows us the price per booklet is high if you're printing a small number. That gets cheaper if you buy more. Okay, what you'll find here, and my graph isn't a very good indication of this, is the graphs are going to cross. So at D, it says, give Marlis advice about how she should choose a printing company. So these actually cross at about 75. And you could do that just by calculating the intersection point of them on the calculator. So doing that second trace, intersect, and then your enter, enter, till you get where those two graphs crossed. So that happens at about 75. So what this is saying is if you want more than 75 books, then you should go with more than 75 books. Then if you take a look at Y2, once you go past 75, it's a little bit cheaper. If you want less than 75 books, so your average price here on graph number 1, if you have less than 75 books, is actually cheaper. Okay, so depending on the number of books you want, and it's based on that intersection point. So D, I'll put it here. If you want more than 75 books, number 2 is cheaper. If you want less than 75 books, company number 1 is cheaper as an average cost. So spending less on the setup fee and a little bit more per booklet is cheaper if you want less than 75 books. But if you want more than 75 books, then spending more on the setup fee and less per book. And you could substitute numbers in there. If you substituted 75 in there, you'd find that your price would be pretty close to each other, and it might be exactly, I can't remember what the calculation is, but if you went to say 70 in both of those, you'll see that the first one is cheaper than the second. If you go to say 90, you'll see that company 2 is cheaper. Okay, so your key ideas here. Rational functions are of the form fx is equal to px over qx, so that's just saying it's going to be polynomials on there. So it could be an x, it could be an x squared, it could be y, whatever variable that they want to use. But it's basically a variable, and your denominator cannot equal 0. So it says rational functions where they don't have a common factor other than one have vertical asymptotes that correspond to the non-permissible values for the function, if there are any. Okay, so your vertical asymptote and your non-permissible values, if there are any, are going to be the same. You can use transformation sometimes to graph these functions and explain common characteristics. You can express the equation of some rational functions in the equivalent form and use it to analyze the graph. So that's like we did in that example 3, I think it was. The important thing to remember is your vertical asymptote is at x is equal to h when you have it in that form. Okay, and it doesn't matter if this is a squared or not on top of here, it's just the general form. Your horizontal asymptote is always going to be at y is equal to k. Okay, now I didn't put questions for you to work on specifically on this one. You can just pick a general number if you want. When you're in class, just ask me which questions to do.